Welcome to Electron Line. Here we have a pendulum that we're going to... I don't even know what to say anymore. Oh, yeah. Okay, again.
No, kitty.
Cat. Okay, I'll get you pet. There you go. Too much fur. No, go. All right. All right. Okay. All right, kitty. Okay, there you go. Okay, let's do this. There. Now. Welcome to Electron Line. Let's now do a problem with a pendulum and conservation of energy. What we have here is a block which is suspended from a railing on the ceiling that is moving at velocity v. Suspended from the block, we have a pendulum of length L and mass m, assuming that the bar here holding the mass to the block has zero mass. We want to know what the initial velocity is of this block because when this block slides over here, it will collide with this other block that's attached to the ceiling, doesn't move, and the pendulum will then swing up and reach a maximum height where at that point it will momentarily be at zero velocity. And so what we're trying to do is, based upon what's given here, based upon the angle and the length of the pendulum, can we express the initial velocity? And of course we can using the energy equation. And what we're going to do here is write it as follows. Any work put into the system plus any initial potential energy plus any initial kinetic energy must equal the final potential energy plus final kinetic energy plus any heat loss due to friction. Of course, right away we realize that the pendulum is not losing any heat due to friction, so that goes to zero, and there is no work put into the system, that goes to zero as well. Initially, the pendulum has no potential energy because it's at its lowest possible height, so we can call that zero potential energy, but it does has initial kinetic energy, which is 1/2 mv initial squared. Final potential energy, yes, because it's gained some height, mgh, but there's no initial final kinetic energy, not initial, but final kinetic energy because it's momentarily stationary, so there's zero final kinetic energy. So the equation simplifies quite a bit. Also, we realize that we can get rid of the mass on both sides, and therefore V initial is equal to the square root of 2 times G times H. Now we're not done yet, because we're not supposed to write it in terms of h, we're supposed to write in terms of theta and L. Now notice, of course, that this is a very familiar equation. Velocity is equal to the square root of 2gh. I'm sure you've seen that before. But now we have to somehow solve for h in terms of L and theta. So what we can do here is we have ourselves a triangle. This hypotenuse is equal to L, and this distance from there to there is equal to L minus h. And now we have a relationship between the angle, the hypotenuse, and the adjacent side, so we use the cosine of the angle. Cosine of theta is equal to, by definition, the adjacent side divided by the hypotenuse, which in this case is equal to L minus h divided by L. So multiplying both sides by L, we get L times the cosine of theta is equal to L minus h. So when I move h across and I move this across over here, we can see that h is equal to L minus L times the cosine of theta. And then if I factor out an L, I get h is equal to L times 1 minus the cosine of theta. And then we can take this and plug it into our equation over here, which means that V initial is equal to the square root of 2g times L times 1 minus the cosine of theta. And that is how we write the initial velocity of that pendulum in terms of L and theta only. That's how we did that.